5 minutes.
Because this one, I guess, I need to cover significant ground.
There's a 2-hour break after this.
So-
But you are keeping people from lunch, so choose your adventure accordingly.
All right, excellent. Thank you all for coming back. We will continue on today's theme of sparsification, and we will use what we built today, what we described previously about graph sparsification, to build fast Laplacian solvers. And as I was saying in the morning, I think it would have been a shame if you had not even seen what is a fast Laplacian solver. I want to tell you what is a fast Laplacian solver. I will definitely be able to show you how to build one. Not the best one, but a reasonably good one, and hopefully basically show you all the elements of the proof. Right? It's somewhat ambitious, but I'll try to stick with it. I'm still happy to take questions, but a request to keep the questions focused on the material. I'm happy to take the generalizations after. Right? We can go to lunch and talk about those. Happy. Super. So let me remind you why we might want to solve Laplacians, right? Yesterday, when we were talking about electric linear systems, we said you can compute the voltages given your current demands, net currents at the vertices, exactly by computing L inverse T. This is what we call solving a Laplacian linear system. So I give you a vector D. You want to give me V, which is L inverse T. And as a simple application, of course, you need to do this in order to be able to solve electrical systems, right? Simple resistive system. But it turns out this primitive is really, really useful. Here are an insane number of applications of fast Laplacian solvers. It started all the way back in scientific computing, finite element methods. And then you can plug these into interior point methods. I should also cite Deitch and Spielman here. I'm sorry, that's not here. You can use it for learning on graphs. Lots of faster flow algorithms, graph partitioning, sampling random spanning trees, graph sparsification. All of these need fast algorithms for solving Laplacian linear system. And the first almost linear time linear solver for Laplacian linear systems is due to Spielman and Teng. And for the amount of influence this work has had on the design of fast algorithms, they were awarded with a Goodell Prize for this result in 2015.
Shout out to Vaidya for Praveen Vaidya for.
Thank you. So thanks for. So there was a time when I was thinking I would do like a history slide of this entire field. I have not had time, but really before Spielman and Teng happened, the idea of using graph structure in order to speed up linear algebraic questions is really due to Vaidya. He built better Laplacian linear systems than solving matrices, right? For graphs, not the best, not almost linear time, but really he introduced the key ideas of using trees in order to speed them up, and really like sort of it's like Dan always cites Vaidya as a big inspiration in all of this. So definitely Vaidya is a key player into how actually this program came about, really. So because once Spielman and Teng happened, this original paper was huge, over 100 pages. It had a lot of ideas that has given rise to many, like those ideas have trickled down into many works and are basically used almost without citation today in the space of fast algorithms. But graph sparsification, Spielman Srivastava that I showed you, originated here in a much more complicated way. Local graph partitioning originated here in a tricky way, which became a subfield of its own, right? And today I will show you a linear system solver that actually does not use any of the tools they built directly, but I mean, all the ideas have sort of been distilled over the 2 decades of work that has followed since. So I hope to show you a much simpler proof of solving Laplacian linear systems in almost linear. Okay, and again, any questions, please feel free to stop me. Super. So before I tell you about the algorithm, I need to tell you that we will not solve these systems exactly. right? So if I wanted to solve Lx equals to d exactly, the answers can be very long. They can require n digits in order to just write down the answer. So we'll not write them exactly, but we'll write them approximately, but with very high precision. And what do I mean? We will return a vector x tilde, which is a delta approximate solution in the following sense. It's not the norm of the error vector x tilde minus L inverse D is delta smaller than the norm of the, this is like the true solution, x L inverse D. Right? So relative to the scale of the true solution, the error is tiny. You should think of delta as 1 over poly n, 1 over n to the 100. Right? So it doesn't have to be constant. It can be really tiny. So which means I can write down log n bits of answer in every coordinate, basically. It's interesting to use the norm, like for convenience, if you would like, you can think of this as the L2 norm. But when doing the proofs, it turns out to be more convenient to work with what is called the norm given by the Laplacian, which is just the square root of the quadratic form with the Laplacian. Right? It's an easy exercise to verify that this is a semi-norm, right? A semi-norm because it actually has a kernel, but that will not matter for most of our applications, right? So under the error measured by the Laplacian, we will give a delta approximate solution where delta is tiny, polynomially small, inverse polynomially small. Is the notion of what it means to approximately solve a system clear? Right, so nowhere are we going to compute the inverse of the matrix. Right, this is key. This is, even though when we are usually taught what it means to invert a system, you say, oh, compute the inverse of the matrix multiplied with the vector. Nobody ever computationally does that. Nobody. Like if you're doing that, you're doing something really wrong. You can much more fast. You have much faster algorithms to compute this product, right? Which is finally a vector that you want to output. And this is called solving a linear system. Right? It turns out that this Laplacian norm is actually the right norm you want to solve it in for many applications, but we'll probably not be able to see that today. So Spearman and Teng originally gave an algorithm that had a large unspecified number of logs, which was estimated around 70. Over the almost 2 decades since, there have been a sequence of works by many people also in the audience here. And finally, Arun and Aaron in 2021 actually achieved an algorithm with a running time of m poly log log. There's not even a log n term. So in some ways, this is really faster than sorting. I mean, I'm cheating because you're working with numbers that have log n bits, but it's some way, but the number of operations is faster than the number of operations you would need to just sort the edge weights. Right, a wrong audience to make that analogy, but you're right, Mikkel. But it's better than the n log n bound for sorting. Okay, I'm going to try to present to you an algorithm that I think is very simple to describe and also fairly simple to prove, especially once you know graph falsification. This is from a recent paper with my student. It appeared at SPA this year. It will not be the best algorithm. We'll achieve m log to the 4n time, but which is usually good for most purposes, right? Like, yes, you pay extra polylog, but what you don't want to pay is m squared. Right, so it's almost linear time, but hopefully the algorithm will be easy to describe, and I'll give you the elements of the proof. Right, and if you're wondering why did it appear at SPA, it's because it's also a parallel algorithm with log squared n depth. Okay, so before I start showing you the pieces, let's just talk about solving a few simple systems of linear equations. One of the simplest ones to solve are what are called well-conditioned systems. What do I mean by well-conditioned? Let's say I want to solve Ax equals b, any PST matrix that is approximately the identity, right? In the same spectral notion of approximation. So all your eigenvalues are, let's say, between 1.5 and 0.5. I mean, that's not what this is, but roughly between a small constant and a large constant, you can do something very simple. You can do the following iterative operation. I start with any initial value x0, and at every step I update x minus what's called the residual, ax minus b. Right? You take the difference and you subtract it from the current estimate, and you just keep iterating. It's a fixed point operation on this equation, right? I want the difference to be 0, but if there's some difference, I'll subtract it from the identity and keep repeating. You can easily show that this converges. How? Let me give you a one-line proof. Look at the difference from the optimal solution. Xi plus 1 minus x star goes from the previous difference, gets multiplied by identity minus a. Identity minus a is a matrix that has eigenvalues strictly between plus 0.5 minus 0.5, or let's say 0.9 and minus 0.9 for convenience. So as you iterate this process, like let me bound this in the norm, you get the spectral norm of identity minus a. As you iterate this process, this error will decay geometrically, 0.9 to the minus t. And you get a guarantee in the same notion of approximation that my solution is close to the optimal solution in the norm measured by the matrix after log 1 over delta iterations, if I want to achieve delta. And this is key for achieving inverse polynomial error, right? If I had a 1 over delta iterations, that's very slow because I have to pay a large factor in order. And log 1 over delta is great. Just paying a log n factor, 10 log n, I can achieve 1 over n to the 10. Is this algorithm and idea clear?
So to get log n, you're going to need to use Newton's method or something. Maybe.
I don't know of anything that gets to log n, right? Because Newton's method for one already requires inverting a matrix exactly. So it sort of defeats the purpose of this, right? Because these operations are not inverting any matrix. I'm just multiplying by the matrix. It's much cheaper. So you have to do log 1 over delta multiplication with the matrix, which is usually very quick, especially if the matrix is sparse.
So the log that you mentioned comes from something. Yeah?
That's right. Those logs are coming from a lot of graph partitioning. But before I say more, Aaron is in the audience and Arun is in the audience, and you can ask them all questions about it. They are very interesting graph partitioning claims that show up, and that's where they pop up. They're not from. Right. So this is a very simple algorithm that solves anything that is a small constant approximation to the identity. You can generalize this a little bit into what is called iterative refinement, which is as follows. If I want to solve a system Ax equals b, I can make it simpler by coming up with a C that satisfies two properties. One, it approximates my original matrix, and two, it's easy to invert. I'm not saying there always exists one, but if you could come up with one that approximates my matrix and is easy to invert, then I would solve a different linear system where I multiply both the sides by C inverse. And now C inverse is cheap to compute, right? And this system has eigenvalues that are close to 1. So you can do the same algorithm, but now with C inverse A, and just writing the explicit iteration and show that it converges to a delta approximate solution in log 1. Right? So this will be our goal. Our goal is going to be that for solving a Laplacian linear system, we want to come up with another system that's easier to invert, much easier, and approximates my original Laplacian. Now maybe that hints to you why we will come up with graph falsification. Right? Is the objective clear? Come up with a matrix C that approximates the Laplacian and is easy to invert. And to do that, we are going to use a tool from the algebra called Bloch-Cholesky factorization. Okay. What is Bloch-Cholesky factorization? Not all of us have seen it, or maybe if you've seen it, we don't remember it. So let's recall it completely. So here's my matrix Laplacian. I'm going to break it up into break up the vertices into two sets, F and T. And that splits the matrix into four components: A, B, B transpose C, right? B, B transpose because it's a symmetric matrix. Like F and T form a partition of my vertices. Given any such partition, Bloch-Cholesky factorization allows you to write a factorization of our matrix as a product of three matrices. Okay, let's read out the factors in just a second, but let me first identify. You have a lower triangular matrix on the left, right? There's a 0 in the top right here. It's block lower triangular, I should identify, right? Well, because you have identity, it's actually completely lower triangular, but it could have been block lower triangular in general. It's upper triangular on the right, and same as transpose of this one. So you get, it's usually also called an LDL transpose, LDLT. This is, you might see this acronym somewhere, LDLT. Lower triangular, block diagonal matrix, transpose of the lower triangular. And I will not, it's easy to sort of multiply these three things and verify that you actually get the same matrix. The focus here is the block diagonal one. The top left block diagonal is the same, A. The lower block diagonal term changes significantly. It's called the Schur complement. And the Schur complement turns out to be C, which was your original matrix in the bottom right, minus B transpose A inverse B. I will keep reminding you of this whenever I use it. It's difficult to see how, I don't have a great way, how would you come up with this from scratch? But if I show you this, it's a very easy multiplication to verify that you get back. This is a very, very nice factorization. Why? Because now you get two nice things. One, you get that when you start with the Laplacian, the Schur complement is also a Laplacian. The proof is not difficult. Let me tell you how, but I will leave it as an exercise. All you have to verify is that the row sums are 0 and the off diagonals are negative and the diagonals are positive, right? These are, you can sort of show all of these three facts. You end up with showing that the Schur complement is also a Laplacian. So that's the first thing. The Schur complement gives me a factorization where the block diagonal has Laplacians. Yes.
It's defined with respect to L and T.
Good. Sorry. Thank you. Sorry. I'm a little too used to this notation, so please. So it's a Schur complement. Let me read this more carefully. So I will end up using some notation. Let me explain. This process can be considered as eliminating the variables f, right? Turns out that this is exactly what you are doing under the hood when you're doing Gaussian elimination. I will not show that connection, but doing Gaussian elimination is exactly this when you eliminate the variables f. And the Schur complement is you have to specify the matrix and you have to specify what are the vertices on which you're taking a Schur complement. So I'll read this as I'm taking the Schur complement of L onto the vertices given by T. Sometimes people use a notation of eliminating, specifying which vertices you eliminate, but I think it's cleaner to think of what vertices I'm projecting the matrix onto. And so that will shrink the vertices I'm projecting the matrix onto. Does that clarify what I'm saying? So it's a Schur complement of my Laplacian onto T. And you get C is the T by T submatrix, original one, and you get T by F, F by F, F by T. right? So it's a T by T matrix on the right. Let's check. Question.
Is there any nice characterization of matrix classes that are closed under Schur complementing?
Excellent question. The question is there a nice characterization of matrix classes that are closed under Schur complement? I can give you an entire book about it, but there are a few rules that you do these operations and it's closed under Schur complement, but it's not complete. And I couldn't find anything interesting that we could try to generalize Laplacian solvers to. Is it clear?
Graph theoretic interpretation of this?
Good. Question is there a graph theoretic interpretation of this? Yes. The interpretation is in terms of, I will show you a second one, but the first interpretation you should think of is that this is doing Gaussian elimination in your Laplacian linear system, right? If I take a variable, I want to eliminate it. So what happens is you delete the vertex and the neighboring edges, and now you put a weighted clique on its neighbors, right? But I will actually show you a nicer interpretation in just a bit. Okay. Why is this factorization interesting? I focused on the block diagonal, but what about these? These are very nice systems, right? They are triangular. They have identities on the triangular, on the block diagonal things. These matrices are very, very easy to invert. In fact, I can just explicitly write the inverse of the Laplacian as now an upper triangular matrix. Here, all I've done is taken the transpose and put a minus sign. That's exactly the inverse of my lower triangular matrix. So you get an upper triangular matrix, the inverse of the block diagonals. So A inverse, Schur complement inverse, and then the lower triangular matrix, which is just the transpose of my upper triangle. Right. So it's a way to express the complete factorization. Yes. And the key point will be that we will pick A that is easy to invert, very easy. Okay. If A is easy to invert, then these parts are all easy. And the question becomes, can you invert the Schur complement? But now the Schur complement is just a smaller graph, so you can hope to recurse.
What is the A plus?
It's a pseudo inverse, but think of it as L inverse, right? Like I was cheating in so far because L has a kernel, so you cannot invert it explicitly. But just think of the L inverse. Like all of the formulas I'm writing are explicitly true with L inverse, with inverse of matrices. If you just completely ignore the all ones direction. So we'll pretend this is the inverse. Right? So does this broad approach help? Right? Like I will need two things: A that is easy to invert, and how do I recurse on the Schur complement? These are the two things I need to specify. Right? So if you do unfold the recursion, what happens is that here's what I'm going to do. I'm going to approximate the Schur complement. I'm not going to build out the Schur complement. Turns out the Schur complement is very dense, the exact Schur complement. I'm going to approximate it implicitly without actually building it explicitly. So that gives me that I get a graph approximation to the Schur complement. And then I will recurse on this Laplacian. In the end, you end up building an approximation to your original Laplacian as a product of lower triangular matrices, block diagonal, and a product of upper triangular matrices. Right? Not many. These will the depth will be log n. So you have log n lower triangular, block diagonal, log n upper triangular matrices. And these triangular matrices are easy to invert. So the meat will be in inverting the block diagonal matrices. And I said approximate. Why is approximate enough? By iterative refinement. By iterative refinement, we said all you need is something that's easy to invert and a good approximation, and we will achieve an epsilon approximation here. So you can apply it. Yes, question.
I didn't understand. How do you get this d many?
Because I recurse on the Schur complement to do a triangular factorization. It needs just a little bit of verifying to work that if I have a factorization in here of the submatrix, you can basically write it as upper triangle again, like full upper triangular matrices outside. Right? That just needs verification because these are all identity, and that really helps with the way it works out. Right?
Use the fact that it's a Laplace.
Good question. So question is, do I use the fact that it's a Laplacian? I will use it at exactly one place. How do you build an implicit sparse? How do you build a sparsifier of the Schur complement implicitly? That will heavily use the fact that there's a graph interpretation and this is a Laplacian. Otherwise, this is a very general recipe and works for many matrices. The other place I'll use it is that finding a submatrix that's easy to invert. Right? If we're given a general PSD matrix, I don't know how to find a large submatrix that's easy to invert. Another question?
D, well, you're going to estimate D, right? It's presumably log.
It'll be log n. We'll basically remove constant fraction of vertices every time. So D is going to be log n. Okay, good. So let's see. So I already mentioned this, that we'll use iterative refinement. So now we need to specify two things. How do you find AI that are easy to invert? And two, how do you build an approximation, a sparse approximation to the Schur complement efficiently and without actually building out the Schur complement, right? I don't even have time to write out the Schur complement. It's too dense, right? It could have all the entries could be non-zero. So I can't write it out. So I need to build a sparse approximation without writing it out.
What is going to be C? C is going to be epsilon?
Yeah, I'll end up with epsilon there.
So you also need to estimate the accumulated error over this.
That's right. That's right. But because of so I need to estimate the error, but because of the multiplicative property of this error, right? I like when taking successive approximations, the errors just add up. So at every step, I will have error epsilon by log n, and I will do that log n times to end up with total error epsilon.
And you're going to aim for just a constant approximation so you can use it as a define.
That's right. That's my goal is to end up with an approximation here that's a small constant, and I can use it to define. Good. More questions? Okay, super. So let's answer the first question. That turns out to be pretty easy. You can find large submatrices of the Laplacian that are easy to invert. And let me show you how. I'm going to find submatrices that are strongly diagonally dominant. Let me define this. So I will say a matrix is 5 diagonally dominant. Like there is a definition called diagonally dominant. Let me not which will be equivalent to 1 diagonally dominant, but I'll just define 5 diagonally dominant. If your diagonal term is larger than 5 times the sum of the off diagonal terms, right? So really it's diagonal heavy. Your diagonal is a constant factor larger than some of the off diagonal terms. It's actually pretty easy to show that for a 5 DD matrix, if maybe this for a 5 diagonally dominant matrix, its diagonal is actually a constant approximation to the matrix itself. Right? It's a pretty easy proof. All you have to observe is that a 1 diagonally dominant matrix is actually PSD, right? So I can write my 5 diagonally dominant as a large diagonal plus a PSD matrix that's smaller, strictly smaller by a factor 4. Like you lose another factor 2 and you get a half approximation. So
you're still sticking to PSD matrices here.
Good. All of my talk I will stick to PSD matrices. Thank you. But in particular, 5DD implies that you are a PC. Strictly positive, definite, in fact, if your diagonals are non-negative. So, but this is great because my diagonal is easily invertible. So I can use it to do refinement again. So this means that if I can find a large 5DD matrix, I can invert it quickly. Right? And that will be an answer to what are my A's. So what I need to show you is that, so like they can be solved using iterative and I should not be seeing all of this together. I need to show you that you can find quickly large submatrices of the Laplacian that are 5 diagonally dominant. Let me just add an animation here so that we can parse this slowly. Okay, how do you find these 5 diagonally dominant blocks? Right, this is just our definition. A diagonal has to be 5 times larger than the sum of the off diagonal. Okay. First observation, a Laplacian is 1 diagonally dominant. Right, the diagonal is the sum of the off diagonals. Right. So this sort of means that if I was to pick a random subset that's small, I expect to see far fewer off diagonals. And that will basically be my algorithm. So here's what I'll do. Right? It's a lemma from a paper from Lee Peng Freeman. I will first start by picking each vertex to be in the set independently with a small probability. Let's say 1 by 20. So it's a large set, right, with high probability. Let me even say it's like exactly n by 20. So it's a large subset. Now, by Markov, if I look at a vertex in A, what is the expected sum of, like not even Markov, what is the expected sum of its off diagonals? The expected sum of its off diagonals is exactly equal to the diagonal over 20 because each of the other terms is included in the sum independently with probability 1 over 20. Right? So I expect to only see 1/20th of my diagonal term. So by Markov, what is the probability that I satisfies the 5DD condition? It satisfies it with 3/4, only fails with 1/4, right? Because it was 1 over 20, 4 times the expectation is diagonal over 5. So by applying simple Markov, I should only fail with probability 1 over 4. Right? So now how many vertices in A do I expect to see failing? 1/4 of the set. Right? So again, with probability half, at most half of it fails. Right? And I apply a second Markov and I get 140 n over 40 size subset. That's 5DD. Yes.
Just for visualization, so
Yes.
this is like the opposite of a sparse cut, right? So you're saying every
That's right.
it's like every vertex.
That's
most of
right.
it's
Fantastic. You should think of 5DD set as a generalization, not as a weakening of independent sets. An independent set would be infinite DD because in that submatrix you will only have diagonal terms. Right? It's a generalization. I can afford some off diagonals, but they should not add up comparable to the diagonal. So you have most of your edge weights going out of this. Thank you. That's a very good way of thinking about these ones. Right? So pick a random set of size n over 20, and then throw out the ones that violate your condition. You will end up with high probability with a set, or maybe with constant probability with a set of size n over 40 that is 5DD. And the good thing is throwing out vertices only improves the 5DD condition for the vertices that you keep, right? Otherwise, I would have a conflict. So since it only improves, everything that satisfies previously will continue to satisfy. Super. So I've specified how to find these large 5DD matrices. You can invert them quickly because diagonal is a good precondition, right? So that checks one key requirement we wanted. So the only thing missing is that how do you build sparse approximations to the Schur complement implicitly? Okay, this might feel a little more mathy, the slides, but I want to say there's good interpretations. Please stop me if the ideas are not clear. But let me pause here to make sure all of us are following. We can recap our process if you want to. We are building iteratively, we are building these approximations, right? We use block Cholesky factorization. You got lower triangular, block diagonal, upper triangular. The vertices we chose to eliminate is a 5DD set, right? So that means that submatrix is really quick to invert. Like the A top left submatrix in a block Cholesky factorization is really quick to invert with the help of iterative refinement. And the only piece remaining is how do I build a sparse approximation, and then I can recurse on the Schur complement. Right? And since I'm finding constant fraction at every step, I'll have log n iterations of recursion. So that is also worked out. The only piece missing is how do I build a good approximation to the Schur complement implicitly. Okay, so let's try to see if we can complete that part. So before we do that, let me reiterate what is the obstacle with the block Cholesky factorization. The key problem is that you get what is called fill-in. This is a language used in the numerical linear algebra community. Whenever you do Gaussian elimination, if you decide to eliminate one variable and it had edges related to 4 of these, when you do the elimination, what you end up with is a clique on all your neighbors. And suddenly the number of non-zeros in the remaining matrix has gone up. Right? You started with 4, now I have 6, but it's a quadratic case. So if you eliminate a high degree vertex, you suddenly get a very dense graph. So we can't even afford to build the Schur complement explicitly. We are going to use the graph theoretic interpretation to build these approximations. To do that, to do the approximation, let me first tell you what is the exact interpretation of Schur complements in terms of graphs and random walks. Okay, let's take this slowly. It's going to have some math, but the interpretation is actually very neat. So I'm just recalling what is Schur complement. We broke up we took a partition of the vertices that broke up our matrices into 4 pieces, right? And the Schur complement is C minus B transpose A inverse B. Right? B transpose correspond to cut edges between F and T. Right? A is the matrix restricted to my 5DD set, right? And remember, this 5DD set has most of its edge weights going outside. There are some staying within. So at every step, like if you were taking a random walk inside A, you will exit it with probability 4/5 at every iteration. Yes. So let's now interpret the Schur complement in terms of random walks. To do that, I will write my A matrix as the diagonal weighted degree minus H. So D is the weighted degree in the original graph, not in the vertex restricted subgraph. It's in the original graph. And H are my edges that stay within the set F.
D is n by n.
Yeah.
Sorry, this is F by F.
Okay.
I'm writing A as 2 F by F matrices.
Yeah.
So it's a smaller matrices. Thank you. Okay. I'm claiming this A inverse, right? A inverse, which is D minus H, right? D is a heavy diagonal, very heavy, right? 5DD. H is these off diagonal terms. It turns out that like the same property we are using for iterative refinement also says, well, all the eigenvalues of H are much smaller when viewed relative to D. So they're like small constants, plus minus 0.5. That means you can actually apply the power series to invert A. Right? All of you have seen the formula 1 by 1 minus x is 1 plus x squared, all right, up to infinity. This holds for x small. You can apply that to matrices when all your eigenvalues are small. So the inverse of identity minus A for when eigenvalues of A are small is exactly identity plus A square all the way up to infinity. And this is exactly what was being used in iterative refinement in some sense, right? You view the iterative refinement as picking the first k terms of the power series, ignoring the rest, and you get error that's comparable to A to the k. So let me apply that power series expansion to this A inverse here. Right? It needs some more manipulation because it's not identity, but you can factor out identity one way or the other, and you get an explicit equality that the Schur complement is exactly equal to C, which is your original matrix entries in the T by T entry, minus B transpose from here. Here's an expansion for A inverse. A inverse looks like, it's worth reading out the first few entries. The first entry is D inverse. The second entry is D inverse H D inverse. The third entry is D inverse H D inverse H D inverse, and so on all the way to infinity. So you write this infinite expansion for A inverse, and you have a B on the right. Let me pause here to make sure all of us at least believe this and are able to interpret what this says. I'll interpret it in terms of graphs, but I hope you see the matrices. Yes, Chandra.
So is it? I mean, you need to have this strong 5DD property to kind of interpret Schur complement.
Good. So the question is, do I need the 5DD property to interpret this inverse? So for Laplacians, it's okay. You need 1DD. Basically, you want the diagonal. You want all the eigenvalues of H to be small relative to the eigenvalues of D, strictly less than 1. Basically, the power series expansion only holds if X is strictly less than plus minus, like within the interval plus minus 1. Right? So the eigenvalues of H relative to D should be strictly between plus minus 1, which is okay for a Laplacian, but not okay for general matrices, general PSC matrices. Yeah, you need connectivity. Thank you. I'm assuming the graph. Thank you, Art. Yeah, sorry, I did not mention this throughout everything I'm doing. I'm assuming that the graph is connected by edges of non-negative weight. That's essential but also it's easy to assume because if it's not, you can invert the Laplacians independently. Yes, question.
You mentioned that this kind of expansion holds for Laplacian.
Yes.
Do we assume that all the eigenvalues of Laplacians are small?
They are not small, but they are small relative to the diagonal.
Does this hold for the entire Laplacian or like?
Yeah, if this, as long as this was 1DD, not even 5DD, then you would get an expansion. But you need sort of strictly 1DD. None of them should have an equality.
Yeah, strictly one.
You need strictly 1DD. You don't, otherwise it will blow up. Okay. This formula you can actually now interpret in terms of random walks on the graph. Right? Before I write down what it is, let's just observe what's happening. C are the edges already exist. B are the edges that are going from like between F to T, right? So think of it as the following. I walk from T to F. Okay. Then D inverse, which means I distribute my probability distribution according to the degrees, and then take an edge inside F. I walk from T to F, take a random step inside F. Like I keep walking inside F until you exit with an edge that comes back to T. Okay. I'll state this formally, just for completeness. But you walk from T to F and you walk inside F until you exit with an edge back to T. And this is exactly formal. So here's a recipe to build the Schur complement exactly. I will take all walks, right? Like a path. You can repeat vertices, you can repeat edges, everything. I'll take all walks that start at a vertex X in T, walk only through vertices in F, right? Like it's all the internal vertices are strictly in F, and then you're allowed to end at a vertex back in T. Take all of these walks and you assign them some particular weight. I'll tell you the weight in just a second, but you assign them a fixed particular weight, add an XY edge with that weight. This is exactly the Schur complement. And it's just by interpreting these terms here. Right? And what is the weight that you put on it? The weight you put on it is a ratio. The numerator is the product of weights of all the edges. Right? If I take X, U, V, Y, I have three edges. Take the product of all the three edges up here. In the denominator, you want the degrees of only the vertices in F. So the two internal vertices, if my walk was length, like if my walk was X, U, V, Y, right? There are total 4 vertices, 3 edges. The numerator has the product of 3 edge widths. The denominator has the product of degrees of only the 2 internal vertices. And that's really popping out of here. Right? All of this is completely coming out of this formula.
Is there a summation of all the walks?
Good. So I'm saying for all walk you add this. So you'll get parallel edges X to Y with different weights. It's not a unique way of specifying an XY edge. You add all possible such XY edges corresponding to a walk. So these are infinite number of walks.
Yeah, I was going to ask that.
Yeah.
So there's an infinite number of edges.
This right now is an infinite interpretation in terms of random walks. I will of course not use this explicitly. Right? But this gives me actually a very simple way to sample them. And here is my Schur complement sampling procedure. So we'll just do random walks. So do the following. So here's a way to achieve an unbiased approximation to the Schur complement by using what we call terminal random walks. So let me describe it visually and then I will show it formally. So here is the blue vertices are the vertices you are eliminating. These are the F vertices. Everything outside is T. Pick an edge. Right? It doesn't have to be entirely inside. It can be crossing. That's okay. But let me show you what happens inside. Now start from one of the endpoints. Take a random walk. So green, 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 green until you exit F. Do the same with your other vertex. So you do purple, 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 and you end up outside. And now I will add an edge here between the 2 endpoints that you obtained with the random walk. Right? Is the process clear to everyone?
Where did you start?
I take 2 random walks, one each from the endpoints of the edge,
Okay.
and keep random walking until you exit F. And the moment you exit F, you stop. I will assign them weights that are as follows. The weight of the new edge that you're adding is the inverse of the sum of the inverses of the weights. There's actually an electrical interpretation for this. If this entire walk, right, combining the green, the orange edge, and the purple, if the entire walk was, if you view it as a sequence of resistors, with resistance is 1 over Wi, then this is the total resistance of the path. Right? So it's really falling out of the electrical interpretation also. It's very consistent with that interpretation.
1 over the resistance?
That's right. That's why there's the phi meaning. Sorry, thank you. So weight is the inverse of the distances, which is the sum of.
And the initial choice weight was random, or what?
You do it for all.
Oh, for all edges.
For all the edges that touch the vertex I'm eliminating, I will do these two random walks until you exit and add an edge there. Right? Let me just write that formally. So for every edge, UV, random walk from U until it hits the first vertex X in T. Right? If U was in T, you just stop. You don't take it. Right? Similarly, walk from the other endpoint until you hit the set outside. And then I will add an edge across these two new endpoints that I've determined, where the weight is given by as a function of the entire walk. So let W be the entire walk that goes from X to U, UV, V back to Y. Right? So combine the two random walks with the sampled edge. That's the entire walk W. And my weight is exactly 1 over the sum of inverses of the weights on the walk. Is the process clear? Can I answer questions?
So you started off, you said you take a node and all its neighbors.
That was the interpretation for eliminating a single vertex.
Right.
Now I'm giving you a Schur complement interpretation for eliminating a block of vertices together.
Okay, so you're saying for every edge.
That's right.
Just to will every edge incident to F, or
Good question. In fact, you can do this for every edge. If the edge was incident to T and T, both the random walks will be empty and you will add the exact same edge. Right? If it was crossing, you will take it just from one side, and if it's inside, you take both. So you literally do this for every edge, and it's the same process. Another question?
I mean, is there anything in particular that motivates this particular design choice for your sampling algorithm?
Yes, but let me take that question afterwards. I think I have the time to basically complete the proof from here. So it's a great question, but let me come back to it. Is that okay? But are you happy with the process currently? Like, so something that maybe we don't have the time to completely prove, but it immediately follows from the random walk interpretation that this process is unbiased. If you take the expectation, in expectation you get the complete Schur complement exactly. And the proof is literally the same. You are basically sampling all random walks. The interesting part is, how does this weight pop out? And let me just say the following, that you will add an edge xy to the endpoints. It will end up it can start from any of the edges on the walk. And each of them will contribute a weight 1 over W1. They will all add up to the original weight. So forget about the weights, but just if I have an entire walk, I can get an edge on xy from this walk, starting from any of the edges on the walk. Right? If I have 4 edges on the walk, each of them could have led to this weight corresponding to the same walk. Right? So I have to somehow distribute the weights between them, and this choice ends up distributing them in the right way. Okay. But so I will not prove it, but it's really just verifying that in expectation, this process generates the same interpretation of the Schur complement in terms of the random walks. Right?
Yeah. While we're looking at this definition and thinking about resistances and thinking about the other talks that happened, is there anything you want to say about Schur complements and vertex sparsifiers?
Good, thank you. Thanks, Aaron. So this is exactly like the idea of Schur complement is an exact vertex sparsifier when you're looking at this L2 problem solving, or the energy of the effective circuit. Right? Sachdeva was talking about vertex sparsifiers. In most problem settings, vertex sparsifiers are approximate, but L2, just like shortest path or the min max that he was talking about, L2 turns out to be a setting, the quadratic energy turns out to be a setting where Schur complement gives you an exact vertex sparsifier, which preserves effective resistances, preserves the energy, if you're only focusing yourself to these subset of vertices that you keep. Thanks, Aaron.
What do you mean by that? For every two vertices U and V in S, that you want to preserve?
For every two vertices in T, the vertices I'm keeping, I want to preserve effective resistances, let's say. They are preserved exactly with the Schur complement. Yes?
Do you need to bound the length of the two lemon walls?
Good. So let's come back to that. Question was, do we need to bound the length? Let's observe some very simple properties of this sampling process. Each random walk is actually log n steps with high probability. Why? Because I'm working with a 5DD set. If from a 5DD set, I will at every step I exit it with constant probability. So it's a very short random walk. In fact, when you sum them all up, you will only get total running time of order m. You don't even lose the log n with that probability, because these are concentrations of sums of geometric random variables. Right? So the total, as long as m is just like greater than log n, you will get concentration that the total amount of time you spent doing the sampling is basically order m. The total number of edges that I get in the Schur complement sample that I'm generating is actually the total number of edges in the original graph, because I drew one sample for every edge that existed. Right? So yes, it gets a little denser. If I reduce the vertices by half, it grows up by a factor of 2, but it's not growing to quadratic, right? So, and I don't expect this process to blow up. It would not be nice if this was 2m. It's really exactly the number of edges that you started. Right? And this thing that I said in words, but you can verify it, it's really an equality. In expectation, you get exactly the Schur complement. Right? And now is where we want to throw back to the previous lecture about matrix concentration. When do you get graph approximation? You need two properties. You need exact expectation, and two, you need each matrix sample has a small norm, epsilon squared by log n. Right? So we have the expectation. So the only piece I need to show, or we need to work through, is can we ensure that each of the samples gives you a small norm, right? Each of the samples has a small leverage score. If it has a small leverage score, then we're done. Then you've actually built an approximation, a spectral approximation to the Schur complement. Okay? In like 3 minutes, maybe I'll run over to a couple more, but it's a very simple proof from here. So how do we achieve Schur approximation? I'm just reminding us that we saw in the first lecture, we want every matrix sample you generate to have leverage score that's bounded by epsilon squared by log n. So if I add an edge E with weight WE, I want WE, effective resistance of E, to be smaller than epsilon squared by log n. If this is true, then I would have built an epsilon approximation to the Schur complement, spectral approximation. The key observation that makes this work is the following, that if I guaranteed that in my original graph, right, I started with an original graph, I'm producing an approximation to the Schur complement. If I guaranteed that in my original graph, every edge has a small leverage score, epsilon squared by log n, then in fact, each sampled edge has a small leverage score, epsilon squared by log n. Same, like if you have a uniform bound on all edges, you get the same bound on all the samples. Why? So let's prove this. It's a very simple proof. And the key is, what was our sampling weight? And this is the inspiration that you were talking about, because we want this to be true. So we will use triangle inequality of effective resistances. I know I didn't prove it. It's an interesting fact about effective resistances, that effective resistances form a metric. They give you triangle inequality. UV, VW, the effective resistance between U and W is smaller than the sum of the effective resistances between the two pairs. Right? I'm not saying leverage scores, effective resistances. Right? This is slightly surprising because the most natural thing you get is actually that the square root of the effective resistances give you triangle inequalities. That's a much easier proof because it's just you can just view them as vectors in L2 space and you get the triangle inequality. But the square one is also true and it can be proven. But we will buy that. Now let me show you with that triangle inequality that I naturally get bounded sample norm. So suppose I'll do it by proof by example. So I started with sampling from an edge uv. From u I took a random walk to x, just one edge. From v I took a random walk to y. I added an edge xy. What was the weight? It's a length 3 walk. My weight is 1 over sum of 1 over wi. Right? So this is weight times the effective resistance. This is the leverage score of the edge I'm adding. Weight times effective resistance. This is the leverage score of the edge I'm adding. I want to show this is small. I'm going to start with the triangle inequality. So I'm going to apply triangle inequality to the effective resistance to say, oh, just apply it all over the path. So I get resistance from x to u, u to v, v to y. This was the path. This was the walk that gave me the edge xy. Right? And I have 1 over wi. Let me rewrite each of these as 1 over w1 times w1r, 1 over w2 times w2r, 1 over w3 times w3r. What have I got? These are leverage scores of the original edges that you actually sampled the walk with. wi, ri, these are leverage scores of the original edges, which I assumed were bounded by epsilon squared by log n. And this is a weighted sum of the leverage scores, weighted convex combination. So this is bounded by epsilon squared. Right? Now the matrix concentration theorem just directly applies, and you're guaranteed that it's an epsilon approximation to the Schur complement. Right? And how do I achieve this? The same trick. I will split every edge into parallel edges that have log n over epsilon squared copies parallel edges, and you scale down the weight. So now every multi-edge has small effective resistance, and when you draw a sample, you will end up with small. Every multi-edge has small leverage score, and when you sample, you end up with a small leverage score. Right? So now we got both the things. You sample with the right expectation. Each sample has a small norm, epsilon squared by log n. So I'm guaranteed that I've achieved a epsilon approximation to the Schur complement. Okay, this is just one iteration, but now you can, instead of working with epsilon, you work with epsilon over log n. And then you get error epsilon over log n, and I can add it up log n times to end up with only total epsilon approximation all the way. Right? So I already mentioned that you can achieve small leverage score by splitting them beforehand. So we recurse log n times with a smaller epsilon to get the complete algorithm. Right? So at the end of log n iterations, you have a factorization with triangular matrices, block diagonal, where every block diagonal is easy to invert, and triangular. And this allows you to write an easy inverse, which is an approximation to the Laplacian. And now you use iterative refinement with the Laplacian to get.
So where are the 4 logs?
Where are the 4 logs? Thank you. So right now, what happened was I got if you replace epsilon by epsilon over log, this gets you a log cubed, and you have to make copies. So you initially started with m log cubed edges, but at every iteration I have m log cubed edges, so I get another log and m log cubed. Right? Okay, let me say this again. So replace epsilon by epsilon over log n. This becomes epsilon squared over log n cubed. So I want to make the initial leverage score to be this small. So I break up each of the edges into log cubed n copies. So right. So now the original graph I'm working with has m log cubed n edges. parallel, like many of them parallel, but I have log n depth of iteration, where at every time I'm working with a graph with the same number of edges, so I get another factor of log n, and that's m log to the 4 running time.
You said there's an implicit representation of the short complement.
I'm building an approximation implicitly, in the sense that I'm not allowed to write down the explicit Schur
But
complement.
the short approximation is explicit.
The Schur approximation is explicit.
You have to write it down every recursion call.
Yeah, that's right. I do write down the Schur approximation,
You
but I'm not
sample
allowed.
once.
Yes, but I'm not allowed to write the Schur complement.
Yeah, got it.
That's all I meant by implicit.
Yeah, I got it now.
I can't write it down and then apply the specification we learned before. Okay, and really that's it. Let me just conclude. We are running over, and I don't want to keep people for lunch, so let me just quickly. So it's a very simple Laplacian solver, right? I basically completed the entire proof, m log to the 4 and running time. You can shave off a log n by using matrix martingales rather than doing matrix concentration, but it just makes the proof messier. But like this is much easier to present, I think. It can be parallelized. You get basically log squared n depth, like log n depth from each, and each operation is just log n depth. You can also improve it by something called black box subsampling based on a uniform approximation sampling paper by Aaron and co-authors. And this gives us a lot of improved parallel algorithms for spectral algorithms. Let me just conclude there. Thank you.
All right.
Thank you. Questions?
So the size of the size of the approximation is m log to the 4th n. You have to do this iteration to actually solve the system, right?
That's right. So
Is there not another factor?
So Bob is asking about what is the size of the approximation. So when I write down L, the Laplacian as a product of matrices, the total number of non-zeros I end up with is m log to the 4n.
And you have to iterate this thing to actually solve the
So
system.
you have a log 1 over delta outside, but that's not a log n over delta. You only, if you wanted to solve it to constant error, you don't pay another log n. Right? But this log 1 over delta is sort of like, that's an additional factor in all Laplacian solvers. All of them basically build an approximation and then solve via iterative.
Can it be done in linear space?
Good question. So
What was
Philip
the
is
question?
asking. Philip is asking, can it be done in linear space? You mean really M space?
Order m, even.
I don't know of anything. I think the best is basically the running time. Okay, there is a partial yes. There exist factorizations that take a lot more time to compute, like that will give you order m non-zeros. But I don't know how to achieve that efficiently. Right? And this algorithm definitely takes m polylog space.
I'm being looked at. I need to think of that during lunch. I'll get back to you.
Yeah.
There is interesting work on log space solvers, which is a whole other different story.
No, but I mean, for practical application, I know it's hard to get them. It's hard to get the practitioners to use this stuff. It's complicated, but I would think that they would care about space.
Actually, that's a very interesting question. So Philip is asking about basically is this practical and would improving the space help? There is actually a bunch of work. So there was a previous version of this kind of elimination-based solver that I had with Rasmus that was eliminating vertices one by one randomly. And Rasmus and Dan Spielman and one of Rasmus's students, they in fact have a paper out and an implementation of that solver that does well in all scenarios. It doesn't beat the specialized solvers that are built for 2D grids, right? But it basically never breaks and gives you a reasonable time everywhere. And they've done a comprehensive comparison to other solvers. It works good, but they are pushing these into practice. Has already been a 2-decade long, and maybe one more decade would do it.
I think not all solvers have a polylog n space increase, but I'm scared to.
Yeah, I mean, even in the computation. even when building it, okay, I don't know of any such one, but yeah, maybe,
Just Cornish design. Oh, the fun thing to debate after break. I'm not
Okay.
entirely sure. I haven't discussed that more after break. Sorry,
Okay.
I said I should wait for lunch, and I.
Okay, I mean, so then,
more questions.
I mean, then the KLOS should also work.
We discussed over.
Does this translate to a distributed algorithm? Like,
Good question. So the question is whether this translates to a distributed algorithm. We tried. This one does not, but there is a different, significantly more involved distributed algorithm, and some of the co-authors are here. Ramos is on that paper. Yeah, there is a distributed algorithm that achieves m polylog running time in the 10x model.
Okay.
But this one does not work. But we were hoping, because it is so simple and
Yeah.
seems local, but the problem is when you take these random walks, now simulating these random walks in a in an efficient way in the distributed network gets very tricky. And that fails. Like at least all the operations we tried, and I'm sure they had also tried it previously, that it just fails. Or not.
All right, well, let's thank Sushant again.
Thank you.
And we now have a lunch break. The next talk will be at 2:00 with Sachdeva. So see you all then.
Thank you.